Hi, welcome to Solve Papers channel. I'm Godfrey. In this video, I'm working out A2 Physics Paper 5. This is about planning, analysis, and evaluation. The paper is 5/1 of May, June 2018. 1 hour 15 minutes is the duration for the paper. You don't need any additional material other than your calculator and your pen. That's all what you require, and of course you're supposed to answer on the question paper itself. That being said, let's proceed and begin. But before we begin, please guys subscribe to my channel and like it, and if you find it useful, share it with your friends so that they also get the benefit out of this paper. Share it widely. I'll be grateful for that. Don't forget also to hit the bell icon. This way you'll be notified every time I upload a new video. Let's get started. Question number 1. As usual, paper 5 has only 2 questions. It has got question number 1 and question number 2. So let's read this out. A student is investigating the forces between two charged metal spheres, S and T. These are two charged, right, as shown in this fig 1.1. Each sphere may be charged by connecting to a positive lead from a power supply to the sphere and then removing the lead. The electromotive force of the power supply used to charge the sphere T is V. Okay, each sphere may be charged by connecting to the positive lead of the power supply. This sphere T is charged with EMF of V. The force F between the two charged spheres may be determined by attaching sphere S to a top of a pan balance, right? A top pan balance. For a constant charge on sphere S, it is suggested that the relationship between the force F and EMF V is given by this expression here, where R is the distance between the centers of the sphere and alpha is a constant. Design a laboratory experiment to test the relationship. We are testing the relation between F and V. Explain how your results could be used to determine alpha. Those are the two key things that we are supposed to be focusing. You should draw a diagram on page 3 showing the arrangement of your equipment. In your account, you should pay close attention to the procedure followed, measurements to be taken, control values, data analysis, and safety precaution, right? So here we need to measure, of course, F. We are told that F is the force between the spheres. It may be determined by attaching the spheres S to a top and balance. So we can list the quantities that we need to focus here and apparatus that we are going to use to measure these quantities. So we need to measure force. That's the first quantity, and the apparatus we need to measure force is the balance. Of course, the balance gives you kilograms. You can convert kilograms into force by multiplied by G. Then we need to measure R. R is the distance R. Distance R. To measure distance R, we need a ruler, meter rule. What else do we need to measure? We don't need to measure EMF. EMF is already in the power supply, but if you need to measure EMF, you need a voltmeter. EMF is measured by voltmeter. Okay, that's it. That's all what we need to, the quantities that we need to have to bear in mind. So look at the diagram here. Distance r is this one between the centers of the two spheres. So the first thing we need to do is we are told that you may draw a diagram on page 2 and page 3, show the arrangement of your equipment. In your account, you should pay close attention to this. When you get correct arrangement of the equipment that you're going to be using to measure your quantities, that makes you 50% successful to your experiment. The other 50% is reading the apparatus accurately. So the instrument that I have in mind here is, of course, I'll tie one of the spheres with a string and suspend it from a fixed point above. Let me call this one T. The diagram should be well labeled. This is a string right there. This is a fixed point. This fixed point could be just a stand, a right-hand stand. Then I have my sphere S here, and this sphere S, I'm placing it on S on a balance. Okay, I'm placing S on a balance. This is my balance. Could be top and balance or even electronic balance. Let me use an electronic balance for my case. Can also use a top and balance. Whatever is available in your laboratory. So I have the screen here. This is 0.0 grams. This here is an insulating material to make sure the charge on S, this is S, the charge on S does not leak. Let me put it on this other side. S, this is S. This is my insulating material so that the charge does not leak. I've used an electronic balance. That is what I have in my laboratory. You can either decide to measure R from the center or from the top. I'll go for the top. Measuring from the top is easier. From top of each of the sphere. This is much easier than the middle. The top is excuse me. Top is easier. It's the same thing. Then here I will have I'll have my extra high tension to charge, which I'm using to charge T, of course, with my voltmeter there, right there. And this is the positive charge, which I'll need to be able to charge T. This is the positive lead to charge T. So EHT basically means extra high tension. This is extra. Let me use capital extra high tension voltage. So when you see EHT, don't touch. That is very high voltage. So I have my diagram there. So the next thing now is to come up here, procedure to be followed, measurements to be taken, control values, analysis, and safety. And therefore I arrange my this in first. I'll define defining the problem. Now, what defining the problem entails, here you only need to do two things. Identify the independent and the dependent variable and the variable that you're going to control. So here I'll say I'll vary v and measure f. Don't forget the equation that is going to help you is this one. We need to vary v and measure f. That is, so f while keeping the control value variable here, while keeping r constant. We need r to stay constant. So this means that v is the independent, and f is the dependent. Variables right there. That is what it takes to define the problem. Next is method. How are you going to collect this data? Method of data collection. How will you get your f? How will you get your r? How will you get your v? Just that. So I'll do this. I'll charge both T and S spheres. I'll charge from the high tension, extra high tension, and record V, that is voltage from the voltmeter, Then I'll go ahead and use a meter rule to measure R. Use a meter rule. To measure R from the top of T to the top of sphere S. Of course, then with S on the balance, I'll zero the balance and read with S on the balance. Of course, I'll zero the balance, zero the balance, zero the balance, so that the balance is really 0, 0. To read mass, of course the mass should read, the balance should read 0 grams when you zero it, so that when there is repulsion, then the balance will be really the force. So with T at distance R, record the mass, M from the balance, Of course, you should convert the mass into force by using this equation. Of course, the mass is in grams. Change it into kilograms and use this equation to determine or to calculate force F. Of course, always remember repeating will help you notice whether you have experienced some errors. So repeat the experiment. Let me call it that. Repeat the experiment for each value of V, and find the average and find average of force F. Okay. Next, we need to show. Now we have our F, and we have our R, and we have our V. So how do we analyze this? So method of analysis. And don't forget, what we are targeting is method of analysis. What we are targeting is this. We want to test the relationship between F and V, and also show how to determine alpha. That is what we should be aiming to do in this method of analysis. So always know that plotting a graph is the best option for you here. So plot a graph. What graph do you need to plot? Of F against F on the y-axis against V on the x-axis. V is on the x-axis. And if the graph is a straight line, if the graph is a straight line through the origin, it's a straight line through the origin, origin is this point, then the relationship which is the relationship, this one, F is equals to R over V over R squared, is valid, otherwise it is not. If the graph is a straight line through the origin, then the relationship, this relationship is valid. Then the relationship, this relationship is valid. Of course, calculate the gradient. Calculate the gradient of the graph. Then use the gradient. Use the gradient to calculate alpha. Use the equation alpha over R, because that is the gradient, is equals to gradient. Of course, the equation F is equals to R over V over R squared. If you compare it to equation of straight line, mx plus c, then F is on the y-axis, x corresponds to V, and therefore the gradient is that is the gradient. Of course, the graph does not have a y-intercept because it's passing through the origin. So therefore alpha is equals to gradient times r squared. To determine a value for alpha. There you are. So we have determined, we have shown that the relationship, how to evaluate the relationship. Remember, design a laboratory experiment to test the relationship of f and v, and also use your results to determine a value for alpha. So we have plotted a graph using our results, then you have calculated the gradient, and using the gradient you have been able to determine the value of alpha. The next one is safety precaution. Safety precaution. You need to consider the procedure that you're using so that you may know what precautions you need to take so that you minimize any injuries. Remember, we are using EHT, very extra high tension. So you need to use gloves to handle the voltage because the voltage is high, right? Don't come into contact with the voltage. Use insulating gloves. Use insulating gloves to handle the high voltage. High voltage positive lead. Remember, you're supposed to charge T while charging the spheres T and S. Of course, you need to place S on an insulating material while on the balance to avoid it getting discharged, to avoid it discharging. And of course, you should also, since T is suspended from a string, so avoid draughts in the room to prevent sphere T from moving while you are measuring both, R and mass on the balance. Those are some of the precautions that you need to undertake. So when you write all those, then this question is usually 15 marks. So there you are, guys. I hope this is of help. Answering this question number 1. Okay. Question number 1 is right there. It's great you're watching these videos, but I encourage you to practice working out these questions yourself. You may get this same paper I'm solving right now from either CIE site or from this site, solved papers.co.uk. You can get both unsolved and also solved papers. The site that I'm talking about is this site here. This is solvedpapers.co.uk. This site here, I need you to come to A level, physics, 2018. These are 2018 paper, AS topicals. Of course, when you get there, this is AS topicals. This is 2019, so AS is A2, sorry, A2 topicals, not AS. 2018. So 2018, we have June, November, and of course some solved papers there. No, this is not topicals, this is past papers, sorry. 2018 past papers. 2018 past papers. It is. Yeah, we have November and June. The one we are dealing with is June. Download this paper. This is the one that I'm solving right now. You can also have a look at a solved version of this paper here. If you need all these other papers, 52, 53 for June and 51, 52, 53 for November, you can get them by clicking this this green button here to bring you to this page. This page is we have paper 5 here. You click here, then you go to 2018. 2018 is there. You can get this paper 5 for both chemistry and physics. Paper 5 June is there, so you click this one to add to your cart. You may ask your parents to help you. This is only costing £10. That's a reasonable price to get these workout papers, to show you how to work out the papers. So get these papers and let's solve them together. This way you will know what the examiner requires. The marking scheme for paper 5 is very sketchy. You may not even know what it is talking about. I've done this, I've taught this for many years, so I know what the examiners need, and I'm going to help you. While at it, if you need my help, I also do I do have online tuitions. I do have tuition classes online. If you need my help, you can get me at this site, spacademy.co.uk. The site I'm referring to is this site here. This is spacademy.co.uk. You can take time and explore the sites. We offer ICT, mathematics, physics, biology, and chemistry. We are helping students from all over the world. You can have a look down here. We help students from Dubai, Abu Dhabi, London, Manchester, all over the world where CIE is usually done. And we have various courses that we are offering right there. So take time and explore our site. I need you to come here. I need you to come right here and download this student guide, and you go through it step by step. It will help you understand how our site works. You may also watch this video to get familiar with our online live classes. If you make your mind you need help, I need you to register. You just need to click here. Of course, you register to create your own account. Once you activate your account, we will send you an email. Give us the correct email. We'll send you a code which you need to activate your account. Once your account is activated, then you sign in, and then from your dashboard you click find a tutor. Then you can get in touch with us. You can get in touch with me. I'll be glad to help you and assist you get your grade A star which you want in physics A level. Very well. Let's continue then with question number 2. Hopefully I'll be seeing you in my tuition class. Question number 2. A student is investigating monochromatic light passing through a diffraction grating. A series of maxima are produced on a screen as shown. These are maximas, right? And the central maxima is right there. Second order maxima is right there. So this is first order maxima. Okay, maximum. So the difference between the central maximum and the second order maximum is S. The student measures the distances between the central maximum and the second order maximum on the screen. The experiment is repeated for several wavelengths of light, right? So, of course, different wavelengths of light give us different colors of light, and each wavelength is monochromatic, is a single color of light. So monochromatic means single wavelength, so single color of light, and they're using a diffraction grating to get this on the screen. The experiment is repeated for different wavelengths of light. It is suggested that S and lambda are related by this equation, where D, this D here, is the distance between the diffraction grating and the screen. N is the number of lines per unit length, this N of the diffraction grating. Then we have S and lambda right there. A graph is plotted of the reciprocal of S squared on the y-axis and the reciprocal of lambda squared on the x-axis. Determine expression for the gradient and the y-intercept. So let's rearrange this equation so that we get a reciprocal of S squared and reciprocal of lambda squared. So the first thing I'll do is I'll flip this equation. I'll flip the equation. Okay, flipping the equation is just bringing the denominator to be the numerator and the numerators to be the denominators. I'll just flip the equation right there. So this becomes 4n squared lambda squared. Then of course this equation here basically means this fraction here basically means s squared over s squared plus d squared over s squared. That's what it means. If you separate it, then we have our this side 4n squared lambda squared. Of course this will cancel to give us 1. So 1 plus d squared over s squared is equals to 1 over 4n squared lambda squared. Alright, I can take this one on the other side. So here I will have d squared upon s squared is equals to this expression 4n squared lambda squared minus 1. Okay, let me bring this one here. So then I will divide both sides by d. So when I do that, I will remain on this side. 1 divided by s squared is equals to I divide here by d, you get 4n squared lambda squared d squared minus 1 over d squared. Of course, I've rearranged this equation. Now I have my reciprocal of s squared here, and I have my lambda of 1 over lambda right here. So this equation is similar to, because we are plotting this on the y-axis and this on the x-axis, mx plus c. Okay, so then our y is 1 over s squared, and then this is right there. And therefore, if you rearrange this equation, if you write this equation again as this, you can write it this equation like this. 4n squared d squared times 1 over lambda squared minus 1 over d squared. So you can see lambda squared is 1 over lambda squared is x. And therefore, the whole of this is a gradient m. The whole of that is gradient m. So m is equals to 1 over 4n squared d squared, and y-intercept, which is c is equals to minus 1 over d squared. Therefore, our gradient here is 1 over 4n squared d squared. Write this nicely. And our gradient is minus 1 over d squared. There you are. Part D of question 2. Values of lambda and s are given in this fig 2.2. You have lambda in times 10 raised to power minus 7, and then s is in meters. Of course, we are taught to calculate the values of reciprocal of lambda squared to the power of 10 raised to power 12 per meter squared, and the reciprocal of s squared in terms of meter squared. In fig this, we fill these columns here. Include the absolute uncertainties of s. So of course you need to get your calculator and you square this, and then you find the reciprocal. Of course, when you do that, these are the values that you're going to be getting. 5.41. This one will give you 4. This one here will give you 4.3. Not 8, 4. 4.34. This one, of course, you're going to do 1, then you square it. Right? This one will give you 3. The bigger the number, the smaller the value of the reciprocal of y. Then this one will give you 2.97. This one will give you 2.60. And then lastly, this will give you 2.30. Now, we go to the values of s, and you can see that the s's have got their reciprocals there. So basically what you need to do is 1 over s squared. We take this value. This will be 1 over 0.62 squared. This will give you 2.6. From my calculator is 2.6, this value. Now, to find the absolute uncertainty for this value, what we need to do is, and by the way, let me show you for y. I think I should just show you that y squared, this is the same as, of course, this is 10 raised to power minus 7. So this is going to be 4.3. If we may use 4.3, so it'd be 1 over 4.3 times 10 raised to power minus 7. Right there. Of course, this is y, so you need to square y. Once you get this squared, when you do that, you're getting 5.41. So you do the same for each one of these values. You take the value, you put it down here, you multiply by 10 raised to power minus 7, you square it, and then you get these values. Now for s, you can see s in meters here, so you put it there, you get 2.6, you write it here, 2.60. Then to find the uncertainty, to get the uncertainty, you take the value of these are absolute uncertainties, you add here, you get 0.62 plus 0.02, what you get is 0.64. And therefore, to get the absolute uncertainty, you find this value of s, the new value of s, and then you subtract it. So in essence, what you need to do is you find 0.62 squared, this one here, minus 1 over 0.64 squared. And of course, when you put your calculator there, you'll get the uncertainty to be 0.16. So that's what you write here, plus or minus 0.16. You go for the next one, you write 1 over 0.72, and you find that squared, of course, 0.72 squared. You calculate nicely, you're going to be getting 1.93. To find the uncertainty of this one, you write 1, of course, 0.72 plus 0.02, you get 0.74. So you find the difference between 0.72 squared minus 1 over 0.74 squared. When you calculate nicely, you will be getting 0.1. So then this is what you're going to be writing here. You write this one, this is 1.93 plus or minus 0.10. Therefore, you do the rest in that way. I'll give you the values for the rest. This is 1.49 plus or minus 0.07. This is 55.8. This is 1.18 plus or minus 0.05. This is 0.9613 SF plus or minus 0.04. And lastly, 0.826 plus or minus 0.03. That's it. So now you've filled the table there. So the next thing is to plot a graph of the reciprocal of s squared against the reciprocal of y squared, and you're supposed to include the error bars. The error bars will be drawn using the absolute values of s, because I mean a reciprocal of s squared, so we'll use this one to plot the error bars. So let's go to the graph below here. We have this graph here. So this graph here is not starting from 0. This is 0.6, this is 0.8, so in between here we have 0.7. This is 0.9, this is 1.1, this is 1.3, this is 1.4. I like inserting this value to make it easier when I'm plotting my graph. This is 1.7. This point here is 1.9. This point here is 2.1. This point here is 2.3. This is 2.5. And so on. 2.7 is here. 2.7. And don't forget, this is S. And then y is down here. You can see reciprocal of y is times 10 raised to the power 12. That is what you got here. Because remember, when you do this, you got this one to be, I forgot to include this one here. This one 5.4. 5.4. 5.4 times 10 raised to power 12. This was power 12, sorry. So the rest, all of this is raised to power 12. Use your calculator and confirm that. And I failed to include that there. Very well. So here we are. We plot our graph. The vast values is 5.4, 5.4. This is 5.5, 5.0 and 5.5 is there. So each one of these is 2. This is 1, 2, 3, 4. So 5.4 is here. 5.4 times 10 raised to power 12. We plot it against 2.6. 2.6 here. So 5.4 is here. 2.6. Right there. Then 4.35. 4.35. So this is this is 4. 1, 2, 3, 3, 4. So 3, 4 is basically somewhere there. So let's go up. 3, 4 is somewhere here. Somewhere there. It's against 1.9 or 1.93. So 1.9 is here. So 1.93. So this is 1, 2, 3. So here. There. Can erase this. The next is 3.5. 3.56 for the reciprocal of lambda. 3.56. So this 3.5. 3.6, 3.7 all the way to 4, so 3.56 is somewhere here. Right, so 1.49, 1.4 is there. This was 1.5. 1.4 is there. So 1.49. So 9 is somewhere here in between there, so I plot there. The next one is 2.97. 2.9 is here. 2.97 is somewhere here against 1.8. So 2.9, 1.8 is here. So there. Somewhere there. Then the next one is 2.6. 0.6 is there. 2.6. Then it's 0.96. 0.96. 0.96 is there. The other one is, the last one is 2.3. 1, 2, 1, 2, 3. 2.3 is there. 2, 3, 2.3 is there. Again, it's 0.83. 0.8. 1, 2, 3. Go for there. So those are our points. So we can now draw the line of best fit. Let me zoom out to get all the points, to be able to see all the points. So let me draw a line of best fit. Just going to draw the line here. Something like that. Okay, line of best fit. So there you have our line of best fit. All right. Then we are taught to include the error bars. Include the error bars. To include the error bars, you draw for 1 over s squared. You draw the error bars at point 2.6, 0.1 above, and 0.16 below, plus or minus. So let's do that. So this is S. So we're going to draw our error bar here. Let me get some different color. So this is 0.16. So each one of these is 0.1, 0. This is 2.7 minus 2.6. This gives us 0.1, and 0.1 divided by 1, 2, 3, 4, 5. Divide by 5. This gives us 0.1 divided by 5. Use my calculator. 0.1 divided by 5 gives us 0.02. 0.02. Right. So each one of the divisions is 0.02. So 0.16 divided by 0.02. This is 16 divided by 2. So this will be 8. So 8 divisions from here. So 1, 2, 3, 4, 5, 6, 7, 8. So there. 1, 2, 3, 4, 5, 6, 7, 8. There. So this is my first error bar. I'll see through there. Very good. I draw another error bar at this point. This is 0. This is 0.10 divided by 0.02. This is 10 divided by 2. This is 5. So 5 lines from here. So let me go for, this is in between here. So this is 1, 2, 3, 4, 5. So 5 is there. So 1, 2, 3, 4, 5. So the other 5 is there. And draw the other error bar through here. You'll forgive my error bars, are not straight, but you're getting the point. For this point here, the uncertainty is 0.7. So 0.7. Sorry, 0.07. 0.07 divided by 0.02. This is 7 divided by 2, which is 3.5. So basically, this is in between here. So 0.5, 1, 2, 3. 0.5, 1, 2, 3. My error bar, the other error bar is there. For this one is 0.5. So 0.05 divided by 0.02. This is 5 over 2, which is 2.5. So 2.5 up here. 1, 2.5 in between there. 1, 2.5 in between there. That's my other error bar. Second last is 0.4. 0.04 over 0.02. This is 4 over 2, which is 2. So 2. So 1, 2. There. 1, 2. There. So that's my error bar. The last one is 0.3. So 0.3, that is 1.5. So it is here in between here. So error bar is up there. In between, my error bar is here. So right there. So the next task is to draw the worst acceptable line. Let me zoom out this. So we need to draw the worst acceptable line. We have drawn the line of best fit. We need the worst acceptable line on the graph. So the worst acceptable line should pass through the error bars. Should pass through each error bar. It doesn't matter whether it is up or down. So let me draw the worst acceptable line. It does not have to touch the axis. You just draw whatever you desire. Sorry. Worst acceptable line. draw that. It is touching all the error bars. All right. I've drawn the worst acceptable line. It is touching all the error bars, so that is good. So you have to label these lines. You have to label these lines. You write, for me, this is worst acceptable line, and this one here is line of best fit. Good. So you have labeled those. That is a requirement. You have to label that. So the next thing is you're told draw the straight line of best fit and worst acceptable line. Both lines should be labeled. We have done that. Determine gradient of the line of best fit. Include absolute uncertainty. Now to get the absolute uncertainty, we'll find the gradient of the worst acceptable line, and then take the difference between the gradient of the best, the line of best fit, and the gradient of the worst acceptable line. That will give us the absolute uncertainty of the gradient. So let's find the gradient. Of course, for gradient, I've chosen these points. Your points should be well apart, and you indicate which points you are using on the graph by drawing dotted lines, and the points should be at least 3/4 of the apart from the from each other on the line. So I'm just going to use my points that I've used to do the line of best fit gradient. So gradient of line of best fit, I've used these coordinates. I've used which coordinates are these? Let me see. I've used these coordinates here. So gradient is equals to 2.2, the y-axis, 2.2 minus 0.3 upon 4.8 minus 2.1. Don't forget to multiply by 10 raised to power 12. Okay, of course you need to be sure to include the units. Here is meters per meter squared. This is also per meter squared, and therefore the units will cancel. When I did my calculations, I got 7.04. You can confirm these guys, times 10 raised to power minus 13. Then worst acceptable line, and then the coordinates that I used is 2 times 10 raised to power 12 for x-axis, and 0.8. The other coordinate was 5.0 times 10 raised to power 12 and 2.24. Then the gradient is 2.24, take away 0.8, and this is upon 5.0, take away 2.2, and this is times 10 raised to the power 12, and what I got is 5.14 times 10 to the power 13. Of course, so the gradient is this one here, so I can as well write it here, 7.04. So what I want now is to find the absolute uncertainty of the gradient of line of best fit. So uncertainty is the difference between this and this. So 7.04 minus 5.14, this one here. Of course, both of these is times 10 raised to power 13. And therefore, what I get here is 1.9 times 10 raised to power 13, 10 raised to power 13. So this is 7.04 plus or minus 1.90, and this is times 10 to the power of 13. So I have my gradient there with the absolute uncertainty. Of course, you need to do that from the graph. As I've said, your points that you pick should be as far apart as possible. You pick points on the line of best fit, you pick points on the worst acceptable line, and then you find the gradient. Very well. Part 4. In part 4, determine the y-intercept of the line of best fit. Include absolute uncertainty in your answer. Of course, you can see the y-intercept. This equation is, this line is not touching here, so of course you should be able to get where this line touches the y-intercept. Of course, when you push this one this way, this line will go this way, so this line will not touch where you are seeing. It will touch much higher. So let's find that. Let's find the y-intercept. Now to find the y-intercept, we use this equation, y is equals to mx plus c, and of course you pick the values of y. You can use this equation, not that equation, whichever. Just pick 2 points on the line. I picked a point 0.3 on the for the y coordinate, and what am I writing now? It's here. Sorry, it's supposed to be here, not down here. So my y coordinate is 0.3, and my gradient, which I've calculated, is 7.04 times 10 to the power minus 13, 10 to the power minus 13, times one of the x coordinate, which corresponds to this y coordinate, which is 2.1 times 10 raised to power 12, right, plus c. Right, so you work out this 0.3 would be equal to, when you multiply this, you'll get 1.4784 plus c. Therefore, c is equals to 0.3 minus this 1.4784. This gives us minus 1.18. That is c. So to find the absolute uncertainty for our y-intercept, we need to find the y-intercept of the worst line, the worst acceptable line. We find the y-intercept, and then we find the difference. That will give us the absolute uncertainty of the y-intercept. Y-intercept of our worst acceptable line. So pick 2 points on that as well. I'll pick 0.8 for y. 5.14 is the gradient of the worst line of best fit. 13 times the corresponding x coordinate on the worst line of fit, which is that, then plus c. Of course, when you work out c here, you find that c is minus 0.33, and therefore uncertainty here, uncertainty for the y-intercept is equals to this value minus 1.18 minus this value, which is minus 0.33. And when you work out, then you'll find the value is minus 0.85. So our uncertainty, the y-intercept is minus 1. The y-intercept is this one here, minus 1.18 plus or minus the uncertainty, which is 0.85. There you go. Part D. Part D. Use your answers in A, C part 3, which is this one here, and C part 4. Determine the values of D and N. Include appropriate units. So A, let's go back to A. A is here. The gradient and the y-intercept. Alright, so we're going to use the y-intercept here to find the value of D. We have found the y-intercept is that. So we use that, and the value that we have determined in y3, y3 was the gradient, which is this one, and then part 4, which we have found the y-intercept. So let's use let's find D. We say that the y-intercept C is equals to minus 1 over D squared. We've gotten the y-intercept here, which is minus 1.18 is equals to 1 over D squared minus. The minus will cancel. Right, so D squared is equals to 1 over 1.8. So then D would be equal to square root of 1.18, and you'll find that D is 0.92, and this is going to be meters. This is going to be meters. So D is 0.92 meters, appropriate units. Then we want N. We want N, and we can find N from the gradient expression here. We have N and we have D. We have already found D, and this is gradient. And of course, we had found the gradient here to be, what is the gradient? Determine the gradient. The gradient is 7.4, right? 7.4. So that's what you're going to be using to find our N. So you know that gradient G, let me use G for gradient, is equals to 1 upon 4n squared D squared. Therefore we want N. So N is equals to the square root. Of course, you take N there, you bring G here, N squared, then you find the square root 1 over 4G D squared. Right? So we substitute the values here. We say 1 divided by 4 times the gradient is 7.04 times 10 to the power minus 13 times D, which you have found to be 0.92. Remember D squared, so you square D there. Then all of this you find the square root. Let me draw a good square root. Find the square root of that. And when you work it out, you find N is 647,733. And the unit is per meter. So you write this one 6.48. Give to 3 decimal places, because all these are 3 decimal places. This is squared. That is squared times 10 to 1, 2, 3, 4, 5 times 10 to the power 5, and this is per meter squared. Okay, work out the unit from this. This is per meter squared. There you have. Part 2. Determine the percentage uncertainty in N. Of course, we know that from the equation for y-intercept, we know that D squared is equals to 1 over C. We also know that N squared is equals to minus C over 4 times gradient, because we know the gradient is equals to 4, remember here, gradient is equals to 4 1 over 4 n squared d squared. So when you make n subject here, n squared subject here, you'll get 4 divided by gradient times gradient, and d squared here is d squared is here. You can make this one, d squared here is equals to 1 over c minus. So when you bring it down here, then it will become a multiplication, then it will become 1 over c squared, which is which comes on top there. Actually, c is not squared. C is not squared. So that's what we are getting, why we are getting this one from, and therefore we can see from here you can get the uncertainty. So it is 2, because it's squared, 2n over n is equals to the uncertainty of the gradient, which is g delta g over g, plus the uncertainty of the y-intercept, which is delta c upon c. Right there, we had found the uncertainty of the gradient here. So we can divide both sides by 2. So we can remove this 2 from here and bring it here, times a half. Okay, so we get it there. So our delta n over n, that is the absolute uncertainty of n, is equals to a half, this a half, times 1.9, which is the uncertainty of the gradient, divided by the gradient, which is 7.04. You can ignore the 10 times 13 because it's going to cancel. This is going to cancel. Plus the uncertainty of delta c, which we have found it here, which is this one, 0.85. So 0.85 over the value of c, which is 1.18, close the bracket. So when you work out this, you're going to get 0.495 is the absolute uncertainty for this delta n. Of course, to get now, this is approximately 0.5. Now to get the percentage uncertainty of n, this is going to be this times 100. So this is going to be 0.5 times 100, and this is going to give us 50%. So 50%. I hope I'm right. 50%, and the uncertainty in n. So there we are, guys. That's how you work out this kind of questions. So I hope this has been of help to you guys. Please share it with your friends so that they may also get help from this kind of work that I've done here. Get more of these solved papers, paper 5, in solvedpapers.co.uk. If you need my help, spacademy.co.uk is where you can meet me. Hopefully I'll see you in my next video. Cheers, guys.